Hello all, welcome to the lecture series in spectroscopy. We here discuss about ultraviolet spectroscopy. Actually, in the previous session, we discussed the electromagnetic radiation, which is a source for this ultraviolet spectroscopy, in which the ultraviolet radiation, which ranges from 100 to 400 nanometers. So what is a UV spectroscopy? A UV spectroscopy exploits the wavelength nature of electrons and its interaction with electromagnetic radiation. That is an ultraviolet radiation which interacts with the matter, that is a chemical substance or a compound, whatever may be, and it can show some characteristic absorption. So we call it as an absorption spectroscopy. The ultraviolet radiation, which started from 100 nanometer and it ended around 300 nanometers. And we can split the ultraviolet radiation in various areas, near ultraviolet, far ultraviolet, and there are various aspects to design. But usually in ultraviolet spectroscopy, the radiation between 100 to 400 is considered as UV. And how the UV spectroscopy works, that is based on the Beer-Lambert's law. So the Beer-Lambert's law defined that an absorption is directly proportional to the concentration. When we increase the concentration, and the absorption is also increases. There is an incident radiation, and after the absorption happens, there will be an outgoing radiation. It's explained by Beer-Lambert's law. We show in the diagram. Here, I naught is an incident radiation. And the incident radiation, when passes through our chemical substance, it comes out. It is called a transmitted light. So we say that the ultraviolet radiation is an absorption spectroscopy. Some part of the light energy has been observed by the substance. And the transmitted light has been coming out, which is analyzed, and how much wavelength it is observed, and what is the intensity is observed. We can analyze it, and we can find that what type of a substance is present inside it. So the Beer-Lambert's law, which says that log I naught by I, that is logarithmic scale of incident radiation, the ratio between the incident light and the transmitted light, is directly proportional to the concentration and the length of the sample container and the molar absorption coefficient. In a simple way, if you put together the absorption is directly proportional to concentration. When the concentration increases, the absorption is also increased. So what happens inside this? So what happens is, we see here some dark lines been represented as S0, that is S0. That will be a ground state. And there is an S1 state. It is an excited state. So the usually H mu, that is an energy we supply. Here we are supplying ultraviolet radiation, but usually we say some amount of energy. It may be a ultraviolet for whatever may be it happens. When it enters into the sample contains some electrons, and the electrons are absorbing this energy, and the electrons get transited to the higher state. So it absorbs and get transited to the higher state. That is S0 to S1. The energy difference between S0 to S1, we call it as E1, E0. E1 is the excited state and E0 is the ground state. The difference between these two, we call it as delta E. So what is delta E? Delta E is the difference between the energy difference between the excited state and the ground state. That means we can measure how much energy is being observed. That energy is equal to H mu. H is a Planck's constant and mu is the frequency of light observed. So based on this equation, we can analyze what type of materials or electrons, whether it is sigma electron or phi electron is present inside that. Okay. And there is a typical instrumentation diagram is given. When the light source is passed through an entrance slit, and from the entrance slit, it goes to a dispersion prism. And the dispersion prism will disperse the things. And we have an exit slit where it converts all the things into a monochromatic light, which is in a required wavelength. And this wavelength is passed through a sample, and the thing which is coming out of the sample container is measured by a detector, which detects how much radiation or intensity is being observed. And based on this energy difference, we can analyze the things. So, I explained this put together, but just we go through some of the important points here. So, ultraviolet spectroscopy is based on absorption of ultraviolet light. We saw that it is based on Beer-Lambert's law. When a molecule absorbs ultraviolet radiation between 200 to 400 nanometers, this happens. So, electron, which is in the lower molecular orbital, that is in the ground state, which means a pi or a sigma bond or non-bond, they get excited to the higher state. The higher state is represented by sigma naught or phi naught. So this is the basic principle. That the sigma bonding, no, from the ground, we have to move upward from lower to up, bottom to up. In the bottom, we put it as sigma. The sigma means it is the electrons present in single bond, and 5 electrons, that means in a double bond, and non-bonding electrons, which the electrons are not being paired and not being involved in bonding. And all the things will observe the electrons and it moves to the excited state. So how much energy is being observed? See, sigma to sigma star is a huge difference. It needs more energy, and pi n to pi star needs a very less energy. So the star indicates it is an anti-bonding level, that is excited level. This is the basic principle behind electron transition happens in ultraviolet spectroscopy. When the ultraviolet radiation falls over the sample, so based on the electrons level, uh, the excitation happens, and the excitation requires some energy. And based on how much energy is observed, we can find out what type of substance is present inside the sample. This is an expanded form, you see. Sigma to sigma star, it is a single bond, carbon-carbon single bond, or sigma to sigma star that requires more energy. And the next one is 5 to 5 star, that is double bond. And both carbon to carbon oxygen double bond. See, carbon to oxygen double bond, it has double bond, and also carbon contains some lone pair of electrons, non-bonding electrons also available. So that involves three transitions. That is N to sigma star, non-bonding electron to sigma, non-bonding electron to pi star, and pi to pi star. So like this, the excitation happens, and based on this excitation, we can identify what is the type of a compound. See, for alkenes, the absorption, that is lambda maximum, the absorption at 177 happens. That indicates N to 5 star transition. So these are some examples. See, the water molecule, when the absorption happens at 167 nanometer, we can say that our compound contains some amount of water molecule. And some compound contain carbonyl group, that is C double bond O group. The excitation is between 186 to 280 nanometers, which involves N to 5 star. So based on this absorption, we can understand the compound nature in our thing, which is we are involving in analysis. And based on this, the ultraviolet spectroscopy has some various application, various fields. That is in pharmaceutical industry. Drug purity test can be done by using this. And in biotechnology, life sciences, protein nucleic acid quantification is done. And the enzyme kinematics, how the enzyme reaction happens. Then polymer studies, it evaluates UV stability and degradation of a polymer, and the thin film analysis in polymers, which is involved in surface coating, and the environmental analysis, which monitors water quality things, which and the air pollution assessment, and food and beverages, in which additives analysis in food, nutritional profiling, and the toxicity analysis in forensic science has been examined. And moreover, document examination has been to detect forged signatures and counterfeit currencies can be analyzed by using this spectroscopy. So the ultraviolet spectroscopy not only used to analyze the chemicals in laboratory, it has a wide application over the various industries, and it's an important thing which is involved in various industries like pharmaceutical, biotechnical, material, food beverage, environment, and even in forensic analysis. Thank you.